things. So in the context of a graph, let's say this is graph with 1, 2, 3, 4, 5 vertices, this edge going through here. It's like a cycle here, then we have this 5 and 2 connected. But anyway, let's call this graph G, and it will have the vertex set V and edges set E. Edge set V, vertex set V. Now, that we have this, what can be defined is a so-called dominating set. And the dominating set usually is denoted D, and it is a subset of the vertex set. But it's not just a subset like any subset, but it has some particular conditions. So I'm going to write them first and then quickly explain what they mean. So, basically, for any A inside the vertex set V of this whole graph G, with removed elements of the subset V of the dominating set, there will exist also some vertex B inside the D, inside the dominating set, such that A and B are next to each other. They are an edge. They're one of the edges of the graph. So what it basically means, a dominating set is to make that dominating set, it will be a subset of the vertices. So it will be basically, we look at all these vertices, we pick some of them. And what must be fulfilled is that these picked vertices have an edge connecting them all to the rest of the vertices. Or not that, for example, if the subset is a 2-element subset, so we say the dominating set is 5 and 2, it's not that both 5 and 2 have to connect to all the remaining vertices of the graph, namely 1, 4, 3, that they have to be connected to these other 3, both of them, but together they have to be connected. So one or the other has to be connected gradually to all the remaining vertices of the graph. That means what here is written a little bit more systematically. So, I mean, this belongs to this A inside V with the D removed, so D is a subset of V. So an example could be 5 and 2, for example. So D could be, for example, 5 and 2. So let's say 5 and 2 is a potential solution here. So 5 and 2, and we have 5 connected to 4 and 1, 2 connected to 3 and 1. So they both connect to 1, but only 5 connects to the 4 and only 2 connects to the 3. But in total, the 5 and 2 have edges connecting them, one or the other, to all the remaining vertices that are not inside the D. And that is the point of the D. So the dominating set for a graph is a subset of the vertices of the graph, such that these chosen vertices have edges connecting them to all the other vertices. So what it means is for any vertex inside the vertices that are not inside the dominating set. So I said 5 and 2 are the dominating set. So for any of the 1, 4, 3 in this case, there will be some vertex inside the dominating set V, 5 or 2, that will have an edge with all these 3. And that is true. For 4 we have 5, 4. For 3 we have 2, 3. And for 1 we have 1, 2 or 1, 5. So yes, 5 and 2 do cover this and do work. But that's not all, perhaps, the possible options. Let's see. So 5 and 2 was the first idea we had. Now we could also try, for example, 3 and 1. So that could also be a possibility. So let's say we choose, so I'll remove the 5 and 2 not to have too many examples at once. So we have 3 and 1. And does that work? Let's see. So, as I said, the point is we choose some vertices of the vertex set and we check if they, one or the other, I mean, we could choose 3 as well, that would work. We could choose the whole set itself and then there would be no vertices left by this to connect to anyway. So it would by default be satisfying. It would be a dominating set. But anyway, let's focus on this other example. So 3 and 1, would it work? Well, 3 connects to 4 and 2, and 1 connects to 5 and 2. So yes, together they connect to the remaining 5, 4, 2. So that's fine. So it works. So we have, for example, 4, we had 3, 1, we had 5, 2, 4 on its own. This remaining one, if we took like unit of the so far 2 examples, 3 and 1 and 5 and 2 that we've had, we would have 4 left. Not that there's like a connection to what we've been doing so far. There was no announcement of the fact that we would like first of all say 5 and 2 is a possible dominating set, and 3 and 1 is as well, and then we take these two we've mentioned so far and we merge them into one set, and then of all the vertices only 4 remains, and for some reason we see that as a pattern or a reason to look behind it for some deeper meaning. Not necessarily, because let's see, does it mean that we have some disjoint sets by default guaranteed, that if 3-1 and 5-2 are both dominating sets, that the remaining must also be some dominating set? No, we have only 4 left, and 4 only has connections to 5 and 3. So it's not that like we choose some disjoint dominating sets and what remains must also be dominating. We see here in a direct context that it's not necessarily guaranteed. And of course, we can have more complicated graphs and we can have more dominating sets. And the probability that one easily can find a dominating set raises with how many edges each vertex has. The graph can get denser. Complete graphs. Basically, if you have a complete graph, definition of it, any vertex connected to all the other vertices by edges has edges going to all the other vertices of the graph. Complete graph. So a complete graph, any subset of it, is basically fulfilling the needs to be dominating set. Because if we take one, if it's a five vertex complete graph, then we can take 2 or 3 or 1. All 3 options would satisfy the conditions to be a dominating set.